Hi, this is a recording to hopefully explain the Bohr model, the tenets of the Bohr model, and how we're going to be analyzing these with respect to quantization of energy. Okay, so in the Bohr model simulation that we did before we started sort of really diving into the Bohr model in detail, we realized that if we have an atom. All right, and let's say we have a hydrogen atom and there's one electron here. And if I have sunlight, right, shining onto this atom, we know that the energy that is emitted by the sun is electromagnetic radiation. So it contains ultraviolet light, visible light, and infrared light. And I can quantify that radiation with an energy, right? That's equal to hc over lambda. I can quantify it with a wavelength and a frequency. Now, this is important because when we talk about Bohr, we're going to be talking about how that energy is absorbed and emitted by atoms and how we actually see that with our eyes. Like, what do we actually observe? All right, so let's say I have my hydrogen atom. And I have this sort of radiation from the sun that is, this hydrogen atom is sort of exposed to this energy. Well, I like to think about the sunlight as radiation, right? It's radiation of electromagnetic radiation. And let's say I have a marble for every single amount of energy that is associated with the sunlight's energy, right? So I have the electromagnetic spectrum, and I know that in that spectrum, we have all different values of energy that correspond to different wavelengths. So let's say I have, there is a marble that corresponds to this energy and this one. And let's say I put all of those marbles like into a bucket. Right, here's my pail. And I'm going to put all those marbles into a bucket so that I have one marble for every energy that the sunlight emits. Okay. And some of these would like be a color, maybe, right? Because that specific energy, like I observe that with my eyes as being a color. So some of these would be sort of like invisible, and some of them would be like have a color, and some of them would be warm, maybe because infrared energy is warm. And let's say I toss all of these marbles at the atom. So I throw all of these marbles at the atom. Well, what Bohr says is that only a certain amount of these marbles will be quote unquote caught by the atom. And the rest of them will just sort of pass straight through, like they'll just not get captured by the atom. And what happens when that occurs is that if I have my electron, here's my nucleus, and the electron is on these orbits. What Bohr says, and that is a really crappy irregular orbit, but these are sort of like circular orbits. So here's the nucleus, and let's say the hydrogen atom, the electron is on that innermost orbit. We're going to call that innermost orbit n equals 1, where n stands for the orbit and 1 is just the integer that defines that orbit. Well, what Bohr said, first of all, is that these electrons can only exist on these orbits. They cannot exist in the space between orbits. And they can only exist on those orbits. So I like to think about that as like, the solar system, we have planets, and those planets have their own defined orbits. There's not anything, they're not like on a little train track going around the sun, they're just on this orbit that's defined, right? Well, that's the way Bohr said the electrons could exist. Those electrons are only going to ever exist on those certain orbits and not anywhere in between. So that was his first tenet. Tenet number 1 is that the electrons exist on these orbits and not in between. The second thing he said was that when these electrons are on these individual orbits, they possess a certain amount of energy. And he defined that energy with the following formula, where the energy that they have when they're on an orbit n is equal to negative 2.178 times 10 to the minus 18 joules times 1 over n, or the integer, squared. So when the electron is on this n equals 1, it has the amount of energy that is equal to negative 2.178 times 10 to the minus 18 times 1 over, in this case, 1 squared. So when the electron is on this orbit, this innermost orbit, it possesses, for e equals 1, negative 2.178 times 10 to the minus 18 joules. Okay, and then when it's on n equals 2, it would have the amount of energy that is equal to negative 2.178 times 10 to the minus 18 times 1 over 2 squared, or a quarter of that energy. And so he said, okay, they're on these orbits, and we say that those orbits are quantized, or the energy that the electron has when it's on a certain orbit is quantized, meaning we can define a value that is associated with it. So that's tenet number 1 and tenet number 2. Tenet number 3 said that if I have, like, say, exposed this atom to energy, then the atom will absorb that energy, right? And that energy is going to cause the electron to move further away from the nucleus. So let's say it moves from n equals 1 to n equals 4, all right? So I like to think about this as like a series of stairs, right? And if you're like right here and you were going to like jump up to n equals 4, well, you would need to absorb energy to do that. Like that requires energy to get further away, like to go up the stairs. And you're going to do this jump, right? Now, you have an energy when you're on here, and you have an energy when you're on here, according to this formula that Bohr described. So this would be the energy of E of sub 4, and this would be E sub 1. So if you're going to absorb that energy, remember the nucleus is back here. And if you're an electron, you have strong electrostatic attraction to that nucleus when you're close to it. And so the further away the electron is from the nucleus, the less stable it is, because those electrostatic attractions are weaker the further away the electron is. So because when the electron goes from this to here, for example, the electron is less stable. And so that means it's going to return closer to the nucleus in order to regain that stability. So now it's going to jump back down to another level. And rather than requiring energy to do that transition, now you're going to emit that energy out of the atom. And so let's say you started here on E equals 1 and you went here to E equals 4. Well, because Bohr defined an energy associated with both of those energy levels, or orbits as he called them, the amount of energy that you would need to absorb to go from E equals 1 to E equals 4 is simply the difference between those two orbits. All right? And in science, we take the change in energy is equal to where you ended up, the final energy, minus the initial energy. All right. Now we can think that as, okay, let's go back up here. I threw all of these energies at the atom. Well, it's only going to catch the marbles that correspond to these specific differences, right? It's only going to catch those marbles that allow it to transition to another orbit. All right, so let's think about that. If the electron started here and went to like there, that would be a different amount of energy than if the electron went there or there, right? All of those discrete differences would be different amounts of energy absorbed. But Bohr said the electrons can never exist there. They can only ever exist on these orbits. So these differences will only ever be finite discrete amounts of energies, meaning that the electron is only going to ever catch certain marbles. And that means that it will only ever re-emit certain marbles, certain amounts of energy back to your eye. Now, what that means in terms of what we observe is that if I have the wavelength, and here's UV, and here's visible, and here's infrared. If I'm looking at the visible spectrum, then this transition here, what I actually see with my eye when I look at the light that's emitted from hydrogen is there's a violet band, there's a blue band, there's like a sort of green band, like a turquoise, and a red band. And these specific wavelengths of light correspond to an energy that is the difference between two transitions. So this wavelength corresponds to an amount of energy that is the result of a transition. All right. Now we know that red light is less energy, and violet light, because it has a shorter wavelength, has higher energy. So we are able to quantify which transitions result in red light being emitted, which transition represents light that is green, light that is blue, and light that is violet. So each one of these specific bands of light represent a specific transition. That transition gives a different value of energy that is absorbed or emitted in order to make that transition. And then if it falls in the amount of energy that our eyes can perceive, then we see that light emitted as a color. All right. When I combine those four frequencies together, it actually produces light that is sort of violet in color. So when I layer all of those four bands on top of each other, it produces violet light, just like when I layer all of the colors of the rainbow on top of each other, like what happens when the sun shines, then we see white light. But in this case, there's only four distinct bands, and those bands produce what we call what looks like to be violet when we actually observe it with our eyes. All right, so those are sort of the four tenets of the Bohr model. And I think the biggest piece here to grasp is that because Bohr has said that electrons cannot exist in the spaces in between orbits, then that means that they cannot hence absorb any infinite amount of energy. And that's why all of the colors of light are not emitted by atoms. Only discrete bands are, because those bands represent the differences in energies of the orbits that they're transitioning between. Now, in real life, what this looks like is because these electrons are moving so quickly and we always have so many atoms, as soon as I turn on the source of energy, that light is emitted instantaneously. And so all of those transitions are happening in the blink of an eye. All right, but if we could slow down the electrons so that we were actually seeing the path of one electron, it would be, grabbing a marble here that's violet and jumping up to this one and then maybe falling down. So it goes from 2 to 6. And then maybe it drops back down 6 to 5 and then 5 to 2, right? So like all of the possible combinations that can happen to that electron basically happen instantaneously. All right. So atoms emit ultraviolet light, they emit visible light, and they emit infrared light in the form of heat. And so what we talked about sort of in the last parts of the activity are which transitions result in infrared, which transitions result in visible light, and which transitions result in ultraviolet light. And that is just sort of based on the mathematics involved there. All right, hope that helps.